Thanks for the introduction. Yeah, I'm glad to visit KAIST again. Okay, so let me begin the talk by explaining the word in the title. So it's basically about arithmetic error value. So I want to study this kind of arithmetic error value in terms of using the dynamics of some special object. Okay, so let me begin the problem, explain the problem. It's about the special error value, mod P. So to do that, let me explain what is a special error value. It's just kind of a special values of error function. So to do that, let me explain some basic object. In this case, a modular curve and some Cusp form. So the German H is the upper half plane. She is just complex number with a positive imaginary part with this metric. So because of that, the geodesic in this upper half plane is just or half circle or vertical lines like this. So if this is a upper half plane, then the geodesic is just a vertical line or just half circle, and the group SL to G acts on this upper plane discontinuously. So in this case, the action is so Möbius transformation like this. Then you can easily see that this is isometry. And then let me consider some subgroup of SL to G in this way. The gamma 0 n is a matrix with these entries, and of course the determinant of this matrix it should be 1. Then x0n, the modular curve, is a compactification of this quotient space by adding the cusp. The cusp this one, and in other words, the modular curve is just you add this cusp to the upper plane, then you quotient by gamma 0 n. Of course, gamma 0 n have action on this cusp again. Okay, so you can it's not easy, but you can see that this is algebraic curve. Now let me introduce the Cusp form, the basic object to build the error function. If you choose a holomorphic one form on x0n, then it should satisfy this relation where this one is an automorphic vector defined by this relation. So basically, this relation should be satisfied for all gamma in this gamma 0 n. So because of this relation, so for example, if you choose gamma as this upper triangular matrix 1, 1, 0, 1, then you can see that this f is invariant by this one. So basically, this gamma gives us a translation of the point. So that means f is invariant by this translation by 1. So that means it has a free expansion. So let's say this is that free expansion. So ANF is the Fourier coefficient of that Cusp form. Then, and the famous theorem by Andrew Wiles and other people is that for an elliptic curve E over Q, there exists some Cusp form such that the Fourier coefficient is equal to P plus 1 minus the FP point of this elliptic curve for almost all prime P. So we are going to study this special Cusp form. So now let me define the error function I mentioned in the title. So for Dirichlet character mod Q, which is just a group homomorphism between this one and this one, now you extend this character to the whole integer by defining other value of chi as 0 when the value, the point is has a non-trivial GCD with a Q. Then you can extend this chi to the whole integer. Then using that function, periodic function, now you define this kind of a generating function, which is given by ANF chi n divided by n to the s. So it's basically Dirichlet series. Now you can verify that this function is essentially a Fourier transform of this new Cusp form, defined like this one. Its Fourier coefficient is given by chi n times ANF. Now you can verify that this is another Cusp form of a level, different level. Then you can also verify that this LSF chi can be analytically continued to C. So basically, this analytic continuation comes from this statement and this modular relation. So combining this one and this one, you can obtain this analytic continuation of that L function. Okay, so let me talk about the special R value. If you now, because you have an analytic continuation, then you can plug in 1 in this variable s. So we can discuss L1 Fe chi. Then it has a very special property like this one. If you multiply the Gauss sum G chi bar and divide by some fixed complex number, depends on the parity of chi, then this number are algebraic. So it's a root of some polynomial with a rational coefficient. So that means it's now topic of number theory. So the definition of this L function is highly analytical. So it has you have some analytic property of this L function, but somehow suddenly if you plug in 1 here, then it becomes an algebraic object. Now we can study this algebraic property of this one. Especially we can study the non-vanishing or vanishing when we divide this one by some prime number p. So we can ask this one. So for fixed prime p and the elliptic curve, how often this algebraic quantity are non-vanishing or not? That's our basic question. Yeah, so it's a simple non-vanishing question, but the same question for the complex situation is a weak version of BSD conjecture. So somehow it has a very important application. We are going to study the residual situation of this important question. Okay, so let me explain how can we study this kind of question. Before that, let me explain several relevant questions for that general question. One is a conjecture by Greenberg, or is a variant of a Greenberg conjecture. Is if L is some prime, then for all sufficiently large p, then this algebraic value is non-vanishing mode p for almost all chi. In this case, character has L power moduli. So it means L power period. So in this case, it has a conjecture and it is still open. So it's I guess 50 years old or 40 years old. And another problem, we can discuss is this kind of a result. So if you consider instead of this L function, if you consider this Dirichlet series, so in this case, Dirichlet series is given by just a twisted zeta function. So now you can verify that this one has an analytic continuation. Then you can consider L0 chi. Then this is actually the algebraic number. So you can also think about the residual value of this algebraic value. Now you can ask how often this one is non-vanishing. And Perron and myself verified that if the character has the minimal period q, the conductor is at the minimal period chi, then number of such chi is greater than or equal greater than the q to the half minus epsilon. And we believe that this is not optimal one, so it can be improved. Anyway, so we are interested in this kind of a result. And question is, can we obtain a similar result for this modular value? So now let me explain how can we study them. Starting point to study such kind of a question is this kind of expression. So let us set m plus minus r as the 1 over omega, the period I mentioned before, is an integration out to infinity. Here, integration is along the geodesic. So this is r, I infinity. Then this one is the integration is along this one. If I mention AB, integration AB, then this is a contour integration along this geodesic. Okay, now I define this one. And now you can see that this one is actually integer. And then for primitive Dirichlet character chi of conductor minimal period, then you can verify that this number we want to study is actually equal to the linear combination of character value and this special value. And this value are actually called modular symbol. And natural question is to study the mod p non-vanishing or vanishing of this value. Now question is, we ask, how are this value mod p are distributed? That's the question. So because this is just absolute value 1. So once you study this value, then you get the information about this one. That's the strategy. So very vague statement. So let me make a concrete one. Okay. So let me now introduce some relevant study for that. Okay. So basic idea is this. I'm going to consider this m plus minus as some random variable on some suitable space. That is a strategy. And let me now explain what kind of a space we need to consider. I mean the probability space. And so that space is this one. So for integer n, let me consider sigma n, which is just a rational number, which is between 0 and 1, of which the denominator is just exactly n. And omega n is a union of them. So it's basically all rational number between 0 and 1, of which denominator is less than or equal to n. So it's a very thick space. So we impose a counting measure Pn on this sigma n and Pn tilde on omega n respectively, and En and Vn the average and variance of sigma n. Excuse me. And En tilde and Vn tilde is average and variance for omega n respectively. Then conjecture by several people as follows. So again, we are going to consider regard m plus minus as a random variable now on this probability space or omega n. And conjecture by Mazur and Rubinstein is a little bit messy, but let me explain this one. For real number between 0 and 1, then the partial sum of this modular symbol like this, divided by the phi n is the limit of this partial sum is somehow this some kind of special value of Dirichlet series. And main point is this. So if you put x equal to 1, then this becomes the average of this random variable. So basically this conjecture means that the average of this random variable goes to 0. And the next question is, the conjecture is this one, Mazur-Rubin. The first conjecture of Mazur-Rubin is for any divisor G of n, there exists some constant C, and some other number, dg, only depends on G, called the variance shift by Mazur-Rubin, and such that the difference between them, Vn, the variance of n plus minus C log n is actually converges to 0. dg, I'm sorry. When n running through all the integer of which GCD with n is equal to G. So this is a first conjecture by Mazur-Rubin. And the last conjecture is this. So basically the random variable is asymptotically normal on sigma n. That is a conjecture. And the exact formula is this. So you make a normalization. So in this case, the average is 0 as expected. So you only have n plus. Divide by this standard deviation. And then this probability of this one is actually the normal distribution. So this is a conjecture of Mazur-Rubin. And these are actually proved by Petridis researcher this year, not this year, a month ago. It's a quite new result, so you can find it in preprint. But point is that this is true for omega n and not sigma n. So actually I expected this result. You can obtain this kind of result. It's doable because of the fact I'm going to discuss later. So I will talk about this one later. Anyway, so they proved this conjecture for omega n. So you see, omega n is just a union of sigma n. So it's a thick space. So rather manageable in some sense. So because of that, they show this one in average sense. In the sense that you put another summation here for n, then you get this one, divide by the another weight. And they also obtain this one after adding this one through n, divided by the weight, then you still get this one. And yeah, and this one for omega n. So their results are basically average version. And they also show that the constant, the C and the G, are related to the residue of some symmetric square function, new function out of this Cusp form. So I'm not going to talk about this one here. Yeah, so again, because they are for omega n, all the results are somehow average version of the sigma n. And another result is this. Kim and myself, the Kim is Myung-il Kim in UNIST. We show that the conjecture of Mazur-Rubinstein, the first conjecture, this one, is true for primes n. So in this case, the sigma n version. And we show this one for prime n when n running through prime number. But that is not that serious restriction, I guess. Anyway, for the proof, we use this kind of approximate functional equation of this integration. This integration can be represented by infinite series. So I don't think I need to explain all the details. So just look at this one. We have this kind of expression. Here, U is the inverse of A modulo n. A is just some real number. Okay, so let me give us some remark of the proof. So the proof for the general n is doable, I guess. It's only laziness, my laziness, not to do that. So I guess it's not that hard to show that. Anyway, so applying the same idea, I mean, using this expression, then I'm working on the Mazur-Rubin one, the first conjecture of Mazur-Rubin. So main term of this variance is asymptotic to this one. So as you can see, you have n plus square. Means that basically you make the square of them. Then you make a square of this one. Now take the average for that. So you expect that then the main term of that multiplication is of this form. And this one is basically symmetric square. And the error term is related to this one. And to study this, we need some circle method to evaluate this one. So that's what I'm doing now. And speculation is, so how about the other moment? So basically, to determine this variable, the random variable, we need to have some older knowledge of the moments of this random variable. Then you win. So we need to calculate this moment of this random variable, and it seems that we can apply this kind of argument to this situation. So that means we may have proof for the second conjecture of Mazur-Rubin. So that's just speculation. Okay, so but this very important Mazur-Rubin conjecture also has some limitation in this sense. So remember, the original problem is this. We want to know how this variable mod p are distributed, but the Mazur-Rubin only give us the information about complex value of this variable. But you see, if in general, if x is an integer valued random variable with a normal distribution, whatever, then if you multiply multiply x by p, then it also has a normal distribution. But if you take the mod p, then it's just 0, right? It doesn't have any. It only have a trivial distribution. So that means we get no information on this n plus mod p from the conjecture of Mazur-Rubin. That's the limitation. So observation is, in fact, it seems that the normality of n plus actually comes from some default phenomenon, namely distribution of a continuous fraction. So that's now what I'm going to talk about. So yeah, I think you already know all the some basic stuff about continuous fraction. Okay, so let me review that. For some rational number between 0 and 1, let's say R has this continuous fraction expansion. A1, A2, AL are digits of this continuous fraction. That means R is written like this. It's a repeated representation of a repeated form of a fraction. And now you have this L. So this L depends on R. So we regard this the length of a continuous fraction L as a random variable on sigma n. So and conjecture is so I'm not sure who conjectured this. I tried to find the literature, but I'm not able to find that. So, but it is you can easily guess this kind of conjecture when you make a computation. So I think it's at least 60 years old or something like that. Anyway, so conjecture is there exist two positive integers such that the normalized excuse me, the normalized probability is in fact is a normal distribution. This one is better in the sense that we have error term, and this error term is optimal. So furthermore, this implicit constant here is independent of x. That's a very good one. Okay, so now you can see the relation between this conjecture continued fraction and the Mazur-Rubin conjecture. There is some relation. I will explain that. Okay, now this is why I think that the Petrus and Resurger are doable. The work, I mean, you can do get some proof for the Petrus Resurger for omega n because it is proved for P and tilde omega n. So Ballard and Vallée show that the conjecture is true for this space, for thicker space. So in fact, what they show is that the moment generating function has some very good expression. So basically, they determine determine this moment generating function itself. So basically, they know everything about the random variable. And the good point is that using this information on the moment generating function, we can show that, in fact, the distribution of this random variable. So the probability that this length of continued fraction is congruent to A, mod P is actually equal to 1 over P plus this error term for some positive gamma. So this is very good. So compared to the Mazur-Rubin conjecture. Okay, so now let me give us some review on the proof. Okay. How many time do you have? Until 5:15. 5:15. Okay, yeah. Now I speak too fast. Okay. So the proof for this one, for the proof of the Ballard and Vallée, consists of two arguments. One is a Tauberian argument in the sense that, so you want to get information on this this moment generating function. Now, one method to get some information on that number is form some generating function. And one example of generating function is a Dirichlet series. So you form some Dirichlet series in this case, of which coefficient is the moment generating function itself. So we consider some Dirichlet series of this form. Then to get the information on this coefficient, we use Tauberian argument. So it means this one. So so basically, I will explain this one in more detail later. But basically, Tauberian argument means this one. If you have this kind of Dirichlet series, then let me explain in a very rough way. If it has a pole, a simple pole, at S equals sigma, then sigma and x an is asymptotic to residue sigma. So this is basically Tauberian argument. Of course, there are some conditions, but let me ignore that. So using the information of the Dirichlet series, now you can deduce some information on the partial sum of the coefficient. So that is the Tauberian argument. So that means we need to study the location of poles and growth rate in some critical strip. I don't explain that. So to get such kind of information on the poles and the growth rate, they show that it has another expression. In some sense, a dynamical dynamical way you can express this one. So to do that, let me give us some setting. So I is just interval, unit interval, and T is a Gauss map defined in this way. And this is a very important in the sense that it generates all the digits of the continued fraction of some given number. So if you express x as this kind of a continuous fraction expansion, then each digit, namely akx, is given like this, a1 t to the k minus 1x. So you repeatedly applying this Gauss map, then you get the digit of the continuous fraction of x. Now let me define some very weird operator called the weighted transfer operator. So for some function which is continuously differentiable on I, and two parameter, complex parameters and w, we define operator hsw in this way. So new function have this kind of value. So hswfx is e to the w times you consider all the inverse image of x under t, then you get this one. Then if you compute this one, then it is equal to this one. Now the relation between this operator and continuous fraction is given here. You can easily see that. You just apply this one several times. Then if you apply this one k times, then plug in 0, then the result is of this form. So you have now k index. I'm sorry, this is 1. And this one is k indices we have. Then this one becomes this complicated one, where pk, qk are case conversion, which is nothing but just case, nothing but the rational number equal to this partial continuous fraction. So in this sense, you can now generate all the continuous fraction expansion by applying this transfer operator. Okay. Then now you can see that if you plug in the constant function in f, then the expression becomes this one. Now you set this one as n. Now you set this one as n, and this one becomes n1 to infinity, n to the s. Now this one is a1, ak, such that qk is equal to n. Now number of such case. So now you can easily see that this number is actually equal to this one. So this is exactly the number of rational number in sigma n. The denominator should be n. So actually this is the denominator. So denominator is exactly n. And in this case, the length is exactly k. So in fact, this number is equal to this one. So you get this kind of expression. Now you add all of them, all for all k, with respect to all k, and you have this one. So it's a summation of this c and k for all k. And then this is just nothing but this c and w. Yeah, here it is. So it's a c and w is a summation of this number and this number for all k. So this number. Then you can see that in fact this one is equal to this one. You have this kind of expression. And now you see that this one is this one. So if you divide this one by this number, then this is average. So this is a moment, basically moment generating function of sigma n. So what you get is this. So we have now some expression for this LSW. Okay, so yeah, here it is. So you have LSW is given in the beginning, and now you have another expression for that Dirichlet series. So now to get information on the poles and some other growth rate, then now we study this one. And this is not number theory area, actually. It's a matter of dynamics. So for me, it's a little hard to understand what's going on here. So this day I'm studying this one. So I hope I get some knowledge on this dynamics and get some information on this one. Oh, of course, in this case, this is done by Baladi and Bali. I'm going to discuss some other general situation of this explanation later. Okay. Now to get information now on the coefficient of the Dirichlet series, we now use this one. So this is a refined version of a Tauberian argument. So it's called the Perron formula. You will see this kind of argument in some very good analytic number theory textbook like Apostol's Introduction to Analytic Number Theory. Then you will see this kind of argument. And basically, it tells us that if Fs Fs is some Dirichlet series with the coefficient an, the partial sum of this an is given by some control integration of this Dirichlet series and this other integrand. Then, and these are some error terms. You take t as an infinity later, or some other variable. So that means you are going to study this kind of control integration. Main idea is you just move this control to right hand side a little bit, then it just touch some pole of this Fs, and then information show up here. So this is basically the result of moving the contour into the right hand side. To do that, we need some kind of analytic or meromorphic continuation of this L function. So this is basically refined version of Tauberian argument. Okay, yeah, the other error term is not that important at this moment. Okay, now what we get. So information on LSW provide us with some behavior of this partial sum of this coefficient. And you see, in this case, this is basically average of sigma n. So the result becomes omega n. So it's an average over omega n. So that's why they are able to prove the conjecture for omega n, not the sigma n. We get is a partial sum of this the Dirichlet series. So that unless we are able to, or there is a way to devise a way to extract information on the AN, single AN itself out of Fs, unless there is such a way, we are not able to deduce some conjecture for sigma n. We need some analytic number theory, development of analytic number theory. Okay, and point is now, so we need to study now this left-hand side to get information on right-hand side, and the left-hand side can be abbreviated like this one, in some sense. So this is a pseudo-inverse of this operator. And basically, because of this form, you can easily see that the pole of this expression lie on S such that the eigenvalue of this operator become 1. So now we try to find S such that this eigenvalue of this one is equal to 1. Then such S, dependent on W, is the pole of the left-hand side. So, so by inspecting this operator, you get some desired information on LSW, which is beyond my knowledge at this moment. That is a completely dynamical state, dynamic area. We need some spectral property of this operator and other property. So very important one. Some estimation on this operator. Okay, so that's it. So that is end of proof. And point is, in some sense, this is a kind of related to Mazur-Rubin, in the sense that that is some kind of a level 1 situation. I will explain what that means. So I want to generalize that the proof of Baladi-Bali to the general level. So let me explain that. So idea is this. What I'm trying to say is this. So let's say this one is the ith conversion of R, so nothing but just this rational number. Then you have this, the integration from 0 to R is the same as this one and this one. So they are same, and they are same. So you get this kind of integration. And if you look at this, some single integration, and then basically you can transform that using this matrix, which is, so if you consider some form of some matrix using this conversion, then it is just a standard exercise in number theory class, undergrad number theory class, that the determinant of this one is -1, I -1. Then putting this one into here, then you get this matrix lives in SL to Z. So let's say this is GI. Then you can see that the image of 0 under this Möbius transformation is this I -1 convergent. The image of infinity is ith convergent. So now this integration can be transformed in this way. I want L, GI 0, GI to infinity, FC dz. And good point is that here the point is that remember that this one is one form on gamma 0 n. So this means G gamma Z0, gamma Z1, so this is an operation, Fz, this is by changing the variable. Now you see this one is equal to F gamma Z, D gamma Z, so this one is equal to Z1, Z, Z, as long as this gamma, I'm sorry, lives in here. So here I consider, so I want to check this GI lives on which right coset of gamma 0 n. So now I count the number of k such that each of GK lives in this single right coset. Then this integration now becomes summation UCUR. Now if GK lives inside U, then that integration becomes this one. So this integration now transforms into here. Now this one is independent of R, the rational number R. So question is now, regarding CU as a random variable on sigma n or omega n, can we analyze this random variable in a similar way as before, as Baladi and Bali did? And the answer is yes, it is. We can do that. So let me give some setting for that. So we need some generalization of previous setting. We need some a generalized Gauss map called a skewed Gauss map, which is the previous Gauss map acts on this interval only interval I, but in this case, this skewed Gauss map acts on this a copy of this I. In this case, the number of copies index of this one. And the action is defined in this way. T star xu is equal to tx, and a1 is the first digit of the continuous fraction expansion of x. Then you define like this, and now you define some auxiliary function in this way. And we have another some tedious definition of this left coset. Then now we need to define a new transfer operator for our situation, which is now the complex variable is the tuple of a complex number, say W and U, which is lives in here, and DM is another matrix. Then for some function which lives in the continuously differentiable function on the this index copy of this interval, then we define this transfer operator like this way. Yeah, so the detail is not that important at this moment. And main point is that can we reconstruct can we represent the new L function? The coefficient of the L function is the moment generating function of the variable Cu. Here Cr is cosec Cr is the tuple of Cur. Now you consider this one, so it's basically vector valued random variable. Now you consider moment generating of that, and consider such Dirichlet series of that moment generating function. Now you can show that this is equal to this one in the same way as before. So taking k1 to infinity, then you now have L star W is this one, and this is really related to moment generating function, and now this one is the summation of the operator, applying this auxiliary function and evaluated at this point. So point is, now we can start the analyzing this value and this value following Baladi and Bali. That means we need to study the spectral property of this operator, or the pseudo inverse of resolvent of this operator. And now we can establish, consider some conjecture on Cu. So we are now working on the spectral property of this operator. That means I need to study some dynamical, dynamics of this operator and spectral property of this one. Okay, and I made some numerical calculation using Mathematica. Then we can see that for each U, some fixed left coset, Cu is asymptotically normal on sigma n. Verify that. And as Baladi and Bali did, we are expecting a proof of the conjecture for omega n. We can do that. I think it's doable. And you see, if x1 and xt are normally distributed random variable, then the linear combination of them is also normally distributed for some fixed number. So that means using this conjecture, we can recover the Petrich and Risager, because you see, Petrich Risager is about the distribution of this number, But this number is actually linear combination of this normally distributed, asymptotically normally distributed random variable. So once we verify that this is asymptotically normally distributed, that means so is this number. So basically, when you prove this, then we can recover the Petri disk resizer. And so omega inversion of Mazur-Rubin, but we can do more actually. As you see before, in the beginning, we have this kind of a result out of this information on the moment generating function. We can do that, in fact. So we can, I think. We are expecting that a result on the distribution of CU mod P. And then now, because of that, we can now expecting a result on the distribution of M plus mod P. So that's how we now study the special value. Okay. Okay, so that's the whole story I want to discuss today, and this is just another wild speculation, which would be easily false, but it's still some dreaming. So, main problem is this: the conjecture for the length of continuous fraction on sigma n is still open. Then can we solve or attack the problem? That's the point. And then some main some dream is this: the powerful argument of Barrett value works only for sigma n. Then how can you attack this omega n? So how can you attack the sigma n? The main observation is this: summation of CUR over U is actually the length of the continuous fraction. And if F is a Cusp form of weight 2 and level 1, then that means this becomes length R times this number. Why? Because of this one. So this becomes equal to just a whole single integral. Now they are all same because level 1. So this becomes CUR. So once we verify that some normality of this one, then you get the normality of this the length of R. And the argument of Kim and myself actually shed some light on the proof of the conjecture for sigma. And so I want to apply that argument to this variable. But there is some problem. There is no Cusp form of weight 2 and level 1. You need to have a level 11 to get some non-trivial Cusp. So this is a empty speculation. And the point is that, but once you giving up holomorphicity, similar object you can expect to live on this upper plane with the action of SL2Z, so-called mass form. It's just eigenform of some eigenvalue of some operator, differential operator, and then in fact there is some mass Cusp form of weight 2 and level 1. So and the one good thing is that in fact, back to our contribution, all this kind of, this circle method actually originate from mass form, calculation in the mass form. I just change or just adapt that calculation of mass form into holomorphic Cusp form. So I think I need back to the origin. So using that, I guess, so I guess we now have some slight hint to study the length of a continuous fraction. Okay, thanks for your attention.